My talk will be based on results obtained during the first workshop at Mathematical Center at Akademgorodok, and will be in many sense a satellite of the previous talk. So let me start with the description of Westphalia-Lehmann algorithm. So all terms of well closures, well ranks, and so on will follow from there. So Westphalia-Lehmann algorithm takes a graph gamma with vertex set V as an input, and as the output we have well closure of this graph. So the first step is the primary initialization of the matrix. So for each pair UV from the squared, we set our coloring or our relation equals to 0, 1, or 2 if this pair of vertices is a loop, edge, or co-edge, respectively. The next step, we compute a multiset for each pair of vertices. In this multiset, we will have some pairs. Pairs will be the colors of vertices U, W, and WV for W in the vertex set. The next step is to transform this multiset into a vector. This following algorithm, the smallest pair in set goes to the beginning, the next smallest pair set next, and so on. And we define new coloring as follows. The colors for different pair of vertices is one smaller than the other if the colors were smaller before, or if our new constructed vectors, the first one is smaller than the second. If the number of colors or real rank at the end doesn't change, we say that this is our veil closure. Otherwise, we return to step 2 and continue this until the size of this coloring stops changing. And I will give some definitions which will help me to demonstrate the working process of Westphalia algorithm, of our implementation of this algorithm, which we programmed during the workshop. So our program can compute parabolics. So let us say that as union will be set of all binary relations of well closure of gamma, and relation from this set is called parabolic if this is an equivalence. And some reminders for definition of strong regular graphs, for Deza graphs, but I think everybody knows that. And some reminders of the process for enumerating strictly Deza graphs. In 1999, the complete list of strictly Deza graphs with at most 13 vertices was presented in a first paper about Deza graphs. Later in 2011, an algorithm for enumeration was presented by Sergei Gurianov and Leonid Shalaginov, and this list was expanded up to 16 vertices. In 2019, this list was expanded up to 21 vertices with new version of this algorithm by Sergei Gurianov, Dmitry Panasenko, and Leonid Shalaginov. And also in 2014, the complete list of Cayley-Deza graphs with A more than 0 up to 59 vertices was presented by Gurianov and Shalaginov again. So let me show how you can use our program, our implementation of this Westphalia algorithm, and at the end there will be some links so you can download it and use it as many times as you want. So let me show you the first example. Here we load our tool, our modular, let me say, the implementation, and we have matrix of Deza graphs with parameters 8, 4, 2, and 1. So this implementation works with Sage Math as a computer algebra tool using Python. So some Python code. So we run function VL, which takes our graph G and returns VL rank and the matrix of VL closure. Let me run this code and you can see the results. And here it goes. So we have VL rank equals to 5, and you can see VL closure over there. So let me show you some time tests. So here I have imported the modular with all strictly Deza graphs up to 21 vertices, and we will see how much time it takes to compute all the closures for these graphs. It takes about 8 seconds if I remember it correctly. Oh, even less. So the time was 6 seconds for computing all VL closures for small Deza graphs. The next example is the time test again, but this time we will not run it. I have done it already. So this is a test for computing all VL closures for Kelly Deza graphs up to 59 vertices. And there are more than 1,000 graphs. I think it's about 1,270 graphs. And as you can see, the computation takes less than 9 minutes for this not a small amount and not so small graphs. So I think it's nice result. Also, our program can compute the VL closure as the set of relations. So let me run this example for you and show the results. So here is the matrix of VL closure, and here is all relations, all pair of vertices. That's goes in relation 0, goes in relation 1, and so on, and relation 4 as a set of lists. And also our modular can compute parabolics for VL closures. Let me run this example. And you can see we have 4 different parabolics. So the parabolic number 0 is every single pair of vertices, and parabolic with number 3 is diagonal. But also we have 2 more different parabolics, and we can calculate them and do our work with them. So actually there are some interesting examples. Example of computation of VL closures, which can lead to an interesting result. So there are 3 non-isomorphic strictly Deza graphs on 17 vertices, and there are still no known construction for those 3 graphs. We don't know how we can construct them, but actually 2 of these 3 graphs can be really easily obtained from one another, and this construction is known, but there are still don't know how to obtain the 3rd one from 2 others. We still don't know how to construct the 3rd one. And really interesting correlation with this observation, we can see the VL closures of those graphs. So let me show you that at the first graph have wheel rank equals 93, and the second and the third graph have wheel rank equal to 83. And actually, the two graphs with wheel rank 83, we know how to obtain one from another, but the graph with wheel rank 93, we don't know how to obtain it or how it connected with second and third graph, but maybe the look on these closures will give us some insights and will help us to make this construction and finally find the way to obtain these graphs. Also, there is the web page with parameters of strictly Deza graphs up to 21 vertices, and web page with parameters of strictly Kelly Deza graphs up to 59 vertices. And if you will look at this page and actually at the table, you can find already computed the closures of those graphs. And if you are interested in it, you can easily browse through there and use it in your research maybe. So for example, these three graphs were just looked at the demonstration program. And for example, there are 37 non-isomorphic graphs, strictly Deza graphs with parameters 26, 2, and 1. And there are many interesting wheel closures over there. So we have wheel rank 42, we have wheel rank 100, wheel rank 200, wheel rank 6, wheel rank 80, wheel rank 400. This is every single pair of vertices has its own relation. We have wheel rank 200, wheel rank 202, and so on. So it's really interesting field of research and field to think why this works there and what we can do with this knowledge. And actually, there is the same thing with Kelly Deza graphs. So you can download and look at the closures for all Kelly Deza graphs up to 59 vertices. And as you remember in a previous talk, Ravil mentioned some two sporadic graphs, two Kelly Deza circulant with 8 and 9 vertices. So we have the table with groups as well, and we can see sort of the cyclic group on 8 elements. Actually, yes, there are 2 graphs, and one wheel closure has rank 4 and another have rank 5. And for graph on 9 vertices, actually, yes, this is the closure with rank 5. There are some other interesting results. Let me return to my presentation. Actually, we have computed all non-circulant Kelly Deza graphs with wheel rank equals 4, for example. Although I won't list them all here because you can easily get them from the web page. But for example, we can see, so there is a hedral group and even symmetric group or some products of cyclic groups and so on. And actually there are 27 graphs up to 59 vertices with wheel rank equals 4. And all the tools I've demonstrated this far are can easily be obtained for your personal needs. So the link to the table of Deza graphs, link to table of Kelly Deza graphs, and actually the implemented vectorial algorithm with our additional functions all can be obtained from different web pages. And I think the example and the presentation will be available for all the participants at the end. And I hope you find these tools useful. And actually, that's all from my side. Thanks for your attention.
Dmitry, thank you very much for your nice talk with useful links. Other questions to Dmitry?
Yes, can I ask?
Yeah, sure, Ilya, please.
Sure.
I am interested in what you can say about your implementation of the Whisper-Lemon algorithm. So my question, can you compare your implementation with what is known somehow?
Actually, I think I could run some tests, and I know you are really interested in the Sphere-Lemon algorithm. So if you can give us some examples, maybe hard to compute examples for the Sphere-Lemon algorithm, so that can take a lot of time. We can check them and say how fast we work. Or actually, you can run it on your computer as well if you're interested. The algorithm is available for everyone. But we haven't tested it in comparison with our implementations. No.
Okay, thank you. I certainly will. I certainly would like to test it.
Thank you.
Yeah.
Thank you.
Okay. Are there any other questions? Okay, Dmitry, would you please show us the page with strictly Kelly-Deza graphs? I just wonder what is the difference between red and green lines?
Red lines will show you that there are no Kelly-Deza graphs on this group.
I see.
So green is group we can construct Kelly-Deza, and red one is we cannot construct. So all links are just red and you cannot use them.
Oh, I see. I see. I see. It seems that you use design which is similar to those Andres Brauer used.
Yes, yes, that was the point.
I see. Did you ask him about this design? I mean, permission to use it?
No, but I think you don't mind.
Okay.
Yeah, it's intentional to look similar.
Yeah, right. Yeah, that's true. Yeah. Are there any other questions? Comments? No? Okay, thank you very much for such an interesting talk with some useful links, and I'm sure that they will be useful in research. Thank you very much.